In this video, we want to introduce two graph concepts, including the graph terminology and representation. First, we see in the real life that many things, many node data, many node objects can be represented as a graph. The networks are often modeled using graphs. The internet network and the social network, right? And custom network and the customer and the product company network, advertising, different type of business, they form the network. All these kind of networks are often modeled using graphs. Graph can be represented as G equal to VE. The reason it is, graph is a data structure. Let me write it down here. Graph is okay, seems it's better to tap. Graph is a data structure which manages objects and object relationship. Right? For example, I give you an example. In the real life, we have different characters, right? So we have Lisa, and we have Trump, we have Clinton, and through the social network, we found out, let's see, we have another one, Brandon, right? I just randomly write down the name, which popped in my mind, and we manage, this is the objects, the different people. And we want to say the friendship. We have a people, and we have, let's use the same color, friendship among these people. Let's see, we have Lisa and Trump is friends, Clinton and Brandon is friends, Clinton and Lisa is friends, Lisa and Brandon is friends, right? Here, right? So it forms a friendship network. And we have to represent this relationship, the objects and object relationship. If we have to represent this friendship, and we need to represent, we have to store the information for each object, right? So let's write it down here. To represent the friendship in the real life, for example, Facebook, right? Friendship in the real life, in the computer. So we have to save. Let's erase this one. We need to represent both objects or object information, right? Object information and object relationship. So in that case, object information corresponding to our V here. This is a connection. This is the side of vertices, and also called loads, right? So with G, the graph, we use the capital, the initial of the graph, equal to V, and this relationship we use E to represent. This is a size of edges. And from now, when we talk about a graph, we would like to write and give a graph G with E, V, and E. In what we have this discussion, V is equal to the connection of Lisa, Clinton, Brandon, and Trump. We read it wrong, right? And E corresponding to the friendship. So we have Lisa to Clinton. We have Lisa to Brandon, right? And we have Clinton to Brandon. And we have Lisa, Trump, right? And we see we use, many of you, if you still remember discrete math, and we use this one to represent, this should be, right? The curly brace, we use this one to represent a connection, a side, right? This is corresponding to the side, as used in Laracana. This one corresponding to side, corresponding to unique, a sequence of, is corresponding to a sequence of unique objects, right? And we use this one to represent tuple, right? Corresponding to order is important, right? Why? The reason here, and it is, if you define E, you need to sure V will exist, right? Because you need to make sure what you have this connection. What happened? So we need to make sure what we have when you make this graph, we need to make sure what they have each nodes, right? This already exists. Then we just need to, this is what we have, the V, right? The total of this one is V. And then, so what we have, this corresponding to, we linked with different vertex and make it E. E, a sequence of paired or vertex pairs, right? Vertex to vertex pairs. So this is corresponding to E, right? This is consists of a relationship of the loads. Okay, so now we would like to go back to here. So graph is G equal to VE. V is a set of connection of vertices, and also corresponding to, sometimes we use loads. Some students, some of us, we are familiar with tree, right? We use loads, and but this graph is corresponding to in the graph theory. In the graph theory, this is one type of mathematical concept, and they use vertices. Let's also use vertices, either one. and E, a connection of edges, and edges, a sequence of vertex pairs, right? This corresponding to, this is not a multiplication, this is the naked tube, and this is the vertex pairs, right? Good. And they have different type of graphs. Undirected graph corresponding to the relationship between the two nodes, which are symmetric. If V is related to V, U is related to V, then we also say V is related to U. For odd V, V not belong to E, corresponding to no self-loops, undirected graph. Direct graph, UV is edge from U to V. This is asymmetric. This relationship is symmetric. And this relationship, since there is no self-loops and even special, right? This relationship definitely may not be symmetric. And we see the relationship really make a difference. If you have V to E, if you have U to V or V to E, there are different edges. Weighted graph, each edge has associated weight given by a weight function W, E to R, corresponding to, let's give you an example, right? We'll see, it's a friendship of different persons, how close they are, or what is the distance between the house. And if sometimes we have to carry out, sometimes we have to remember the edge weight, we call it edge weight, right? And to use it to represent different information. For example, let's say the distance of two houses, and we remember here, this is 5.7 miles, and this is 3.1, this is 1.0, this is 35.9 miles, right? The miles. So we can, put some specific weight on the edge and use it to represent the difference of different quantity information, quantity value associated with the edges. Same thing here. Sometimes even for each load, we can use to hold the different specific quantity information. So in this case, we say once you have the weight associated with each edge, then that is corresponding to weighted graph. And in the graph, sometimes we see dense graph and a sparse graph, which dense graph corresponding to each node almost related to any another nodes, and the sparse graph is in the opposite way. And why does it make sense? We say here, if you have n nodes, given n vertices, if you give n vertices, then in that case, the maximum number of edges, right? It's n choose 2, and which is corresponding to 2 of n times n minus 1. So this is corresponding to O n squared. You remember? So this reason, when you see the graph is dense corresponding to the number of edge close to O n squared. If it's sparse, it means it's small and very small. Okay, and this will also prove that if UV belong to the edge connection, then the vertex V is adjacent to vertex U, with the graph is a collection of V and E. Each one is a connection, and V corresponding to the connection of vertices is a connection of vertex pairs. Adjacent relationship is symmetric if G is ungraded. Not necessarily so if G is directed. If G is connected, there is a path between every pair of vertices. E greater than V minus 1. That is makes sense, right? If we say G is connected, the graph is connected, it means for every pair, you could have one path. You could have more than one, but at least you need to have one. It's connected. It's reachable. Every load is reachable, right? It's reachable for every load. Furthermore, if E equal to V minus 1, then G is a tree. Why? The reason it is because in the tree, there is no cycle. And the graph is allowed with no cycle. If there is no cycle, we connect n vertices, and you only have n minus 1 edges connecting n nodes, right? Because in the tree, every two nodes could have one path. You just have not more than one, just one path. So the n vertices we can use n minus 1 edges to connect n vertices. There are two different types of representation of the graphs. First one, adjacency list. And since we have G equal to V and E, and we have to represent V, we have to save all the information of each vertex. So this is idea from the adjacent list. We use one specific array to save each vertex, and then we use the linked list from each element in that array to represent who is connected with this A. For example, given this graph, A, B, C, D. First, you make the array. You have 4 elements, and A, B, C, D. And later, we use a linear data structure, linked list, to represent A is connected with B. A is connected with D. A is connected with C. Here, the order of these 3 nodes do not matter, because once it's a friendship, you really don't care about and which one is the first one, right? If there's no special application there, no special needs there, right? And let's take a look. C. How many nodes connect with C? A, B, D, right? So C connected with D, C connected with A, C connected with B. So this is adjacent list. And we also have adjacent matrix, which corresponding to the design of this representation. The people who designed that, people think about if that graph is quite dense. And in almost every 2 nodes has connection, then very intuitively, and we can use the matrix. We can use just like Excel table. You have multiple rows, multiple columns. Each row represents 1 node here. Each column represents 1 node here. If you have 4 rows, you have 4 rows, and also have 4 columns. Each number in row and column, this number, represent the vertex 1 is connected with vertex 2, right? Let's use A, B, C, D to represent. And here we also have the number, right? So this is corresponding to A is connected with B. Excellent. And A is connected with C, right? And A is connected with D. And B is connected with C. And C is connected with D, right? And since this is an undirected graph, and once you have A connected B, and also you could have B connected with A, right? Just like a friendship. They are symmetric. If you draw a line here, you see this is symmetric. A to B, B to A is the same number. So we use 1 that's not 0 represent low connection. If it's 1, represent they do have one connection. So this is an undirected graph, and both adjacent list and adjacent matrix. And actually, you can also use these two methods, can also use to represent directed graph. It will be the same. Consists of array ADJ of V lists, one list per vertex. For U belong to V, and adjacent U consists of all the vertices adjacent to U. If weighted, stored weights also in adjacent list. If that's weight here, and stored weights are also in adjacent list. This makes sense, right? So it means you will save the specific weight in the each linked load. Now the question is, for I smaller than I from this. Now the question is, how can you write the code to represent these two, right? For I from 0 through n minus 1, because it starts from 0, then you have n minus 1. Walk us through the adjacent list of loads, I, and then you can make this adjacent list and adjacent matrix. For direct graph, sum of the length of all the adjacent lists, which is equal to V. The total storage is V plus E, right? It makes sense, right? Because which represent the linked list in and through each specific vertex information, and this element has one linked list to represent the outgoing edge corresponding to this load connect with which load, right? So in that case, it is the total for the direct graph will equal to E, and the total storage is V plus E. For undirected graph, sum of the length of all the adjacent lists are double E. Total storage is still V plus E. So the adjacent list, the advantage, it is when the graph is sparse and that is space efficient, can be modified to support many graph variants. And the disadvantage it may not be efficient if the operation for finding specific edge very frequently happen, right? Because you have to go through each specific linked list to find one. And so in that case, this is not efficient. This is not efficient because to find a specific edge, you need to have all V plus E time, right? If we use this one to represent number of vertices, yes, we use this sign to represent number of edges. And let's see adjacent matrix. If you have given the graph and we represent in the adjacent matrix, we have V times V matrix A, number of vertices from 1 to V in some arbitrary manner. A is then given by Aij equal to Aij equal to 1 or 0. If ij belong to H, then aij is 1. Otherwise, it's 0. In this case, you will find out it's very easy to locate which A vertex is connected with B vertex, right? Because this is a two-dimensional array, and you just use a constant term to access specific edge, so easy to find the edge. And the storage, they need the storage is n square. No memory efficient for large graphs. To list all the vertices adjacent to U, take V, theta V term. To determine if UV belongs to the edge with the constant term, can store the width instead of bits for weighted graph. This is two graph representations. They also have another different graph terms. Parse. Parse graph usually sometimes we see the parse in the graph. Parse corresponding to they have a reachable. For example, we see from A through B, right? A to B, and from A, B is reachable from A. In that case, we see they have a parse. And the parse length corresponding to number of edges. For example, from A to F, so the parse length is 2. From A to D, from A to D, the parse, it is 4, right? So parse AD is equal to 4. And parse AF is 2, right? Simple parse corresponding to all the vertices is different on that parse. So this is a simple parse, this is simple parse, and if we have this one, do you think it's a simple parse? No, that's not simple parse because they have a cycle there. So this is not what we want when if the people want simple parse. This is not what we want, right? Okay, cycle. Direct graph. The cycle, this is very obvious, the definition. In direct graph, they have a cycle is a part of the parse, just not simple. V1, V0, go to the V1, and all the way go to the Vk, right? And it forms a cycle if V0 equal to Vk and k greater than or equal to 1. So here we do not consider the self cycle. So in this case, this is one cycle, right? From B is a cycle, from B to F to E, and to B again. This parse form a cycle. Once you have a cycle, you can list this way in a different way, right? You can see we're starting from F, F, E, B, F, F, B, E, F for the direct graph. And the same thing for direct graph. And direct graph. And when people talk about connectivity a little bit different. Every pair of vertices is connected by a parse in the undirect graph. In the connected undirect graph, one connected components, directed graph, which is strongly connected direct graph. Every pair of vertices is reachable from each other. One strongly connected components. For this concept, once we know in the specific assignment, if we have, then in that case we will give you more discussion. And this is some very common concepts, especially the parse cycles, direct graph, undirect graph, and with dense graph, sparse graph, and this representation G equal to VE, and this is very popular to be used. And also here we talk about the adjacent list to store our graph for the direct graph, for this direct graph, and also for this indirect graph, right? And use adjacent list and also adjacent matrix. And that's all for this video.